Good morning, everyone. We're going to have another podcast here on section 13.2 using the ideal gas law. So the ideal gas law, again, we're talking about that it's really hard to study these gases because they just vary so much in terms of pressure and temperature. And so sometimes they will simply just cut to the chase and say, you know what, we're going to combine Boyle's law, Charles' law, and Avogadro's law, and we are just going to use the ideal gas law. Now, the interesting thing about ideal gas law, and you probably did a little bit of research on this when you were doing your Boyle's law activity, there was one question there, and it said the difference between ideal gases and real gases. Now, we are living in the world of real gases, and they interact, but the ideal gas law takes that away, so that's a little bit easier to study our gases. So the formula that you have here, you can see it's all the variables that we have used all along, and that is not going to be changing. And so we have PV equals nRT. Some of the older kids, you may have heard them say PIVNRT. That's kind of how they abbreviate this. So P is for pressure, V is for volume. This time it does have to be in liters, so highlight that, and I'll talk about that in a second. N is for the number of moles, and then we have T for temperature, and yes, that has to be in Kelvin. That is not changing. And then we have this gas law constant. And what this is a fudge factor. This is the way that we can compare the different types of gases. So this gas law constant, this is a constant, it should be on a gold sheet, and it's 0.08206 liters atmospheres per mole Kelvin. So because of this, we have to have our pressure in atmospheres in order if we're going to use this gas law constant. We have to have volume in liters, we have moles, which is moles, and we have temperature, which is in Kelvin. So essentially, this isn't a hard law to use. You just have to understand a little bit what it means. So if you have some space, I don't know, you might have some space here on the paper that you can squeeze it in. We need to understand that gases behave ideally at low pressure and high temperatures. Well, if I show you a little of this graphically, I always think it's nice to see things graphically, that if we say PV equals nRT, and this is just what our gases are going to look like over here, and then on our x-axis we have pressure, and this is going to be in atmospheres. Atmospheres. And then if we talk about this line of just being one, where all these things are equal, that this line right here is going to be our ideal gas. And so this is where they want gases to behave at so that we can study them a little bit easier. Now what actually happens is we are living in the real world, and not all gases behave ideally. So I just said that they behave ideally at very low pressures, which 1 atmosphere, which would be way down over here if this is my 0 point, and I want to make this at like 200 atmospheres, and this would be at, I don't know, 400, it doesn't really matter. After that, you'll see the difference, is that they behave very ideally at this very low pressure of 1 atmosphere and fairly high temperatures. And high temperatures is anything above 0 degrees Celsius. So we're not talking things that are extremely hot. So gases that, that we are accustomed to. Well, if we take a look at good old hydrogen, it really does behave ideally at 1 atmosphere pressure, but the minute you start adding more and more pressure, it deviates far away from the ideal gas. And what they figured out is this happens for all sorts of gases. We have carbon dioxide that actually raises to almost a similar point, but at anything above 100, it dips way down like this, and then it behaves ideally again at those lower pressures. And so this green line is carbon dioxide. And I have one more here that I want to show you. Let's grab another color. Let's see, what do I got? I got black. And if we take a look at nitrogen. Nitrogen is the one that actually acts more ideally than any of the other ones. It stays a lot more constant, very, very close to this ideal gas until we get all the way out to almost 200, and then it shoots up. And this would be nitrogen. So again, it's just showing you these different gases that the ideal gas law really only works at very low pressures. Okay, so let's take a look at this and put it into a calculation. So let's see, where's our sample? I went right by it. Here we go, our example. So we have a sample of hydrogen gas, has a volume of 8.56 liters, so we have the liters that we need. We have a temperature of 0 degrees Celsius and our pressure. So the first thing that we have is we have volume, and that's at 8.56 liters, so I have the unit that I need. We have temperature at 0 degrees Celsius. That is not going to work, so I'm going to add 273 to that to get it into Kelvin. And then I have a pressure of 1.5 atmospheres. And it wants us to calculate the number of moles. Okay, so when I have all of these variables and I want to find the number of moles, I know that I can use the combined gas law. So I'm going to use PVNRT, or PV equals nRT, and go ahead and just substitute in again. So I have 1.5 is my pressure. My volume is 8.56 liters. And I do not know what the number of moles is, so that's going to be my X. And I have my gas law constant, so here where you put it in, 0.08206 liters atmosphere mole K. And then times my temperature, which is 273 Kelvin. And I can go ahead and do my magic algebra that you guys are all very good at. And when I find that, I got the number of moles to be 0.57. Okay, so that's our ideal gas law. Again, it's just another formula that we need to try to work with and understand gases and how they behave. So if you go ahead and do this practice problem on page 459, you should get an answer of 26 degrees Celsius. And here you should get an answer of 1.8 atmospheres. All right, then I'm going to do one more thing on Dalton's law of partial pressure, because this is another quick little law. So again, all of this, we talked about Dalton's law of partial pressure. We've talked about this already in class, that the total pressure of a mixture of gases is the sum of the pressures of each gas in the container. We talked about it in the classroom, that our classroom is a mixture of the nitrogen gas and the oxygen gas, and then 1% of all the other gases that we have, which we found out was a really good thing. So that when I took my scoop of air, it didn't matter if I took my scoop of air in my classroom or out in the hallway, then the gases are continuously mixing. Another great thing is we talked about that we don't have these pockets of oxygen gas that we have to make sure that we are breathing in to ensure our life. And so these gases are continuously mixing. And each gas exerts the same pressure it would if we're alone. So Dalton's law of partial pressures, which is something that you probably already understand, it's not going to be a big woohoo moment. It's just that my total pressure is going to be equal to the pressure of those individual gases. So in my example that I'm using, the pressure of oxygen you're feeling right now, and nitrogen, and then the 1% of every other gas that we have. Many times we collect it over water, which is what we did in class, and we probably already talked about how you need to correct this when it's over water because of the vapor pressure that water does exert on a gas. So there's the correction factor that I'm sure that you will already have seen by this point. So here we have our practice problem. This one on page 467, I do want to do in class because there's a little trick there, but I am going to assign to you this one on page 469. And when you are done with this, you should get that the nitrogen, or the number of moles for the hydrogen gas is 0.0188 moles of hydrogen. All right, saved by the bell. Look at that. You guys have an awesome day, and I will see you soon.